Okay, welcome everybody. It's a pleasure to see you guys here, and it's my big pleasure to welcome Minghui Diao. Little background for those who don't know her all that well. Minghui is a tenure-track assistant professor at the Department of Meteorology and Climate Sciences at San Jose State University in California. Her research, and we hear a fair amount about that, her research interests include using in-situ and remote sensing observations of clouds and aerosol to improve model simulations on various scales. She received her bachelor at Peking University in 2008 and her PhD in Princeton in 2013, where she had received a NASA Earth Science, Space Science Fellowship and the Francis Upton Fellowship at Princeton University. I got a NASA some long time ago. And after her PhD, she actually moved here to NCAR and spent 2 years as an ASP before she got a nice job in San Jose. So today's talk is about clouds and aerosols, linking aircraft measurements, satellite observations, and model simulations. Please, let's welcome Minghui Diao.
Thank you. Okay, thank you everyone for coming to my seminar. I hope I'm speaking loud enough. So today I'm going to talk about quite a few different sections that we do in my research group. That includes clouds and aerosols, and we're going to use both aircraft measurement, in-situ measurement, and satellite remote sensing observations to evaluate and compare with different scales of model simulation. So first of all, I want to thank all my students who actually contribute to quite a lot of the work that I'm going to show, and including my former student, John DeLisandro, who recently graduated and just started his PhD study at University of Oklahoma, and Catherine Stanlon, who's sitting here, Ryan Petnall, the first-year graduate student, April Alberto, Qing'an Yang, Jackson Ip, who are 3 undergrad students in my group. So besides my students, I have a lot of collaborators along the year, including many people right here from UOL at NCAR, such as Yang Jensen, Britton Stevens, Andrew Gettleman, and also from other University of Wyoming, of Xiaohong Liu, Chenghai Wu, and also back at MCube, George Brown, Hugh Morrison, and many, many other collaborators. And I also want to thank all the funding I got from NSF and NASA for support my group. So here's an outline. I want to talk about the climate impacts of cloud, but specifically I want to focus on the influences of relative humidity on cloud characteristics and processes. And for the instrumentation I use are mainly based on the water vapor hygrometer called the VXL hygrometer, which is the one that I'm actually calibrating this summer in collaboration with UOL. And the observations I will use are mainly from several NSF campaigns that is on board the NSF Gulfstream 5 research aircraft. For the analysis, there will be 3 main sections. So if you pay attention to the 3 structure, you probably wouldn't get lost in my talk today. The first section is ice nucleation in deep convective clouds. The second one is a totally different region, Southern Ocean, cloud phase, and relative humidity compared between in-situ observations and CAM5 simulations. The third part is very different from the first 2 parts. It is about the California surface PM 2.5 derived from NASA satellite data and how we use to guide local air quality management. So in the end, I want to highlight at each section, I will give a summary and ongoing work, so you won't get lost to the very end. So this picture is a picture, many people use it, and I have shown this many times as well, but I want to bring this up today because it really gives the point of why do we care about clouds for climate impact. So this is a picture from IPCC AR5. In the first few rows, you have anthropogenic greenhouse gases, their radiative forcing. If you add those rows up, you get a positive 3 watt per meter square, which is a warming effect on the climate. And if you look at the other little bar right here, which says cloud adjustment due to aerosols, the problem right now is not only we do not know this bar very well for its magnitude, but also the direction still has large uncertainty with this large error bar here. And on the other side, if you think about the global cloud net forcing, which is a negative 20 watt per meter square, this means just by doing a simple math, a 15% change in the global cloud radiative forcing could either double or cancel out all the anthropogenic greenhouse gas effect just by this little change in cloud cover. So with that overarching statement, I want to highlight the role of relative humidity on cloud radiation and parameterization. So there is a keyword for part of my talk. It's called ice supersaturation. This is where relative humidity with respect to ice is greater than 1. And this is also the prerequisite condition for ice crystal formation in cirrus cloud. If we have in the real sky observation, we have two types of condition. You can see supersaturation. One is a clear sky ice supersaturation here. The other one is ice supersaturation being in cloud. But then sometimes in the simulation, there could be biases for representing these two conditions. They could either put in fake clouds that shouldn't have been there, or they could put clouds that are existing with more ice, and that would generate a difference in the radiative effect. From the study that we did in 2016 by China et al. 2016, when we calculate the radiative effect for mistaking ice supersaturation as ice crystals, it leads to an average 2.5 warming effect on the TOA radiation. And here is the figure. You have the TOA effect on the left-hand side, and you have the influence from different ice water paths that you put in the model. And a second example I want to show out is this parameterization of ice cloud fraction in the NCAR CAM5 model. So this is based on the equation from Gettleman et al. 2010. So you can see it's very sensitive for how much cloud fraction of ice cloud you have in the climate model, depending on what kind of relative humidity threshold you choose. And sometimes these thresholds could be very arbitrary. And that pose the question of how can we improve this arbitrary selection by using observations to validate it. The third example for relative humidity's role in cloud simulation in CAM5 is this comparison study that Dr. Liu and Dr. Wu and me, we did on this collaborative work in 2017. So we compared the HIPPO global campaign in-situ observation with the co-located and nudged CAM5 simulation. By nudge, I mean we nudge the CAM5 meteorological condition towards the geosphy reanalysis data. And here, all the cross markers show where we actually see real cloud in the observation. And the shading in blue and green shows where CAM5 see ice cloud in blue and liquid cloud in green. And the arrow here, I point out where you actually misses a lot of cloud over the Southern Ocean in this time segment. And we break it down, this segment, into three parts. We try to understand, is the missing cloud due to the missing variability in temperature or due to the missing variability in water vapor? By breaking it into relative humidity, water vapor, and temperature comparison between the model and simulation, we see that it is the missing variability in water vapor highlighted in the second arrow that actually contribute to the lack of clouds over this Southern Ocean segment. So all of these studies give us an idea that not only we have to understand how much water vapor is in the sky with good measurement from in-situ observations, but also using highly accurate measurement, we could help to improve climate model simulations. So the instrumentation I use, this is the vertical cavity surface emitting laser. It's called the VCSEL hygrometer. It is a near-infrared laser working at 25 Hz, and we use 1 Hz data throughout all my analysis today. It has accuracy of lower or equal to 6%, precision lower or equal to 1%, and combining with the uncertainty in temperature, which is plus minus 0.3%, we can reach a range of RH ice and RH liquid uncertainty for the different temperature range we sample. Besides the water vapor instrument, I also rely on several other cloud probes, such as the Cloud Droplet Probe CDP, the Fast Two-Dimensional Probe, 2DC, which measure totally different dynamical ranges, and I also use King Hot Air Probe raw icing rate indicator for evaluating mixed-phase cloud. For all these analysis, it has a horizontal resolution about 100 meter to 250 meter, depending on the true airspeed of the aircraft. And here is a picture on the left-hand side with the VCSEL hygrometer hanging halfway out of the aircraft. So this is the laser box, which is inside the aircraft cabin, and then the blue fin, which has the optical depths between here, directly measure what the air is flowing between the mirror. And on the other side, we have on the wing pod, which is the fast 2DC and the CDP probe that I often use. So this summer, we actually got the support from the ASP Faculty Fellowship. So I was able to bring my three students and I to NCAR and stay here for a month. And during my visit here, I'm collaborating with several scientists at EOL to do the calibration of VCSEL hygrometer. This is the foothill chamber that we're using, which is located downstairs of EOL right here in this building. And then the other diagram is just to show how we set up this calibration. We put the VCSEL hygrometer separate into two parts. So now it's in two pieces. The laser box is outside the chamber. The blue fin, which has the optical depth part, is inside the chamber. We sealed up this optical depth part in a housing, and then we use the environmental chamber to control temperature. And that way we get a certain temperature to mimic what is in the real atmosphere. And I want to have special thanks to help from Stuart Beaton, Laura Tudor, and Hendrik Gilmer, who helped me with setting up this chamber. So some of the analysis that we have done in the past few weeks, I just put it together yesterday because we are still taking a lot of time to collect a lot of data. For individual temperature data point, it takes about 4 hours to get equilibrium. So you can calculate during even a 4 weeks time, we don't get to do a lot of these data points. But on the other hand, I was able to do two sets of full temperature calibration. One is cooling down from 0 to minus 65 degrees. The other one is warming back up from minus 65 to 0. So we were able to not only test the hysteresis of this temperature calibration, but also we were able to get a stepwise function of different temperature between the VCSEL and the one calculated based on the temperature probe. So the physics behind our calibration is we can define saturation vapor pressure only using one factor, which is temperature alone. And the factor of temperature, we rely on an RTD semester that Stuart brought in, and we use that as a reference value, and we convert into saturation vapor pressure using the accurate temperature measurement. And then we separate the calibration into 3 different modes, because the VCSEL hygrometer works as 3 different modes in order to measure a 5 orders of magnitude difference of water vapor, including the weak mode, direct mode, and the strong mode. For each mode, I use a polynomial fit to get what is the ratio of water vapor mixing ratio with respect to the reference value. And then using this ratio, we can then apply to the raw data, such as to the Socrates campaign, to adjust the water vapor using this QA/QC method. One thing I want to point out is I'm actually pretty happy to see that the hysteresis test of cooling down and warming up in the purple and red color actually agree relatively well with each other. This gives us confidence that this type of calibration is repeatable and you can get consistent result. Another calibration that I did is to compare the 2 temperature probes, VCSEL temperature probe versus RTD. This has nothing to do with the water vapor measurement, but there is another temperature probe on the VCSEL hygrometer. So I calibrate these 2 temperature probes because when we fly, we also get the temperature data from the VCSEL probe, and we can see using this calibration by putting the 2 probes next to each other side by side, we have about difference of minus 0.5% to 2.5%, and this is actually converted in terms of the water vapor mixing ratio. On the other hand, I also give a ballpark estimate of what is the uncertainty associated with this chamber calibration. This is to say, do you know your chamber would bring in extra uncertainty that would probably deviate from the truth? And that is because when we calibrate, we cannot put the RTD probe in the housing right next to the mirror optical depth. We have to touch the housing on the outside while the VCSEL is sealed inside. So the difference between the inside and outside wall will give a difference about 1% to 60% from 0 to minus 65 C. And this will help us to give a range of uncertainty to this type of calibration. Now, all the way to the scientific question now. So I'm going to talk about the first section, which is ice nucleation in deep convective clouds. So this is a study that we did in 2017. We do a comparison between WRF simulations and DC3 observations. So the DC3 campaign happened in 2012 from May to June. This is all the flight tracks in the NSF Deep Convective Clouds and Chemistry campaign. So we combine all the flights together, and then we compare with real simulations from WRF using two nested domains. One is 800 meter, the other one is 2.4 kilometer. We tested 4 double moment microphysics scheme. The first one is the default Morrison double moment scheme. The second one is actually slightly modified Morrison scheme by changing the Cooper parameterization threshold to 125%. I'll explain later about this one. And then the third one is the default Thomson 2008 scheme. The fourth one is a Thomson and Eidheimer aerosol aware scheme. And this figure just shows where you are likely to see supersaturation. We color code the picture from light gray to dark gray that only show where you are ice supersaturated from 100% to 150. And then we overlay it with the positive and negative vertical wind, which is in red and blue contours respectively. So what this picture is showing is the May 19, 2012 case. And as the squall line develops, we see all the wavy structures that has the up and downs of vertical velocity. At the same time, we have a lot of supersaturation happening around the convective event. A comparison between the simulation and observation is done this way. First of all, we put observation on the top, and we separate it into in-cloud and clear sky. On the y-axis is the RHI, relative humidity, with respect to ice. On the x-axis is temperature. And you can see we restrict all the analysis to this part to below minus 40 degrees C. So this is all ice crystal, no supercooled liquid water. And then we also do the same separation for simulation. On the left is in cloud, on the right is clear sky. And if you just do a one-to-one comparison, you can see some of the simulation, like the Morrison double moment scheme, has a cutoff for clear sky supersaturation at 108%, while the real observation actually still see a lot of variability of relative humidity up to 150%. Similarly, when we have the Thomson 08 scheme, it has a cutoff at 120%. So when we dig into the parameterization of ice nucleation in WRF, we find out the activation of Cooper curve is the main control over this threshold. And when we set the Cooper activation to 125% relative humidity, it immediately lifts up this cap on the RHI distribution. And among all the 4 double moment schemes that we're testing, the Thomson aerosol aware scheme shows the most comparable RH distribution in terms of this analysis. Another way we test how ice crystal is being initiated is to see how much supersaturation is allowed in the simulation. Just to remind everyone, ice supersaturation is a prerequisite condition to form ice. When you have ice crystal being formed, it is because there were ice supersaturation that reached a certain threshold. So we tested the probability for you to see ice supersaturation in different simulations. And I know this has a lot of information, but keep in mind, just to do a simple one-to-one comparison in the red box that I outlined here. So if you see the observation is the first row, and the 4 different schemes of simulation are the second to the 5th row. And what you have here, black is the downdraft, and different color line all the way to red is higher and higher magnitude of positive vertical velocity. The observation doesn't seem to show much of a separation between downdraft and updraft, how much supersaturation you would see. This is only probably 1 order of magnitude difference. But the simulation, on the other hand, show very large separation in terms of probability of supersaturation. And this gives an idea that this separation means the simulation relies more heavily on using higher updraft to initiate and maintain supersaturation. So another cloud resolving model simulation that we did is to use the NCAR CM1 idealized squall line simulation. So the CM1 model is based on the a setup from Bryan and Parker 2010, Bryan and Morrison 2012, we use an idealized squall line scenario with periodic lateral boundary and open boundary conditions in the cross-line direction. So to keep it short, how do we compare a model simulation with aircraft observation? In this CRM simulation, we put in mock aircraft. So that means for every 1 hectopascal of the simulation, we put in a mock aircraft that keep flying in the same direction, back and forth, just as if there is a real aircraft sampling horizontally in the atmosphere. And we get 451 mock planes to compare with the observation. And we tested 3 different horizontal resolution. The first one is 250 meter, the other one 1 kilometer and 4 kilometer. Just from a first look, you can already see the 250 meter simulation is much more realistic when we compare the size of the supersaturated region, which is outlined in the dark green color, compared with the size of the real observation. And when we quantify the size of the supersaturated region, remember the size of it will probably determine the size of the ice crystal to be formed in this region. We actually found there is a positive correlation between the size, ISSR length, and the maximum RH inside the supersaturated region. And when we put all of the simulation in different setup to compare with the top left corner, which is the one Hertz observation, we find the one that matched the best is actually the modified simulation with a higher threshold to initiate ice nucleation at 130%. So this backs up what we found in the WRF study. The nucleation that is based on the Cooper parameterization actually initiate too early to have too many ice, and that will actually lower the relative humidity dramatically, like from here to here or from here to here. And none of the other parameters could actually help to improve this, such as we tested the vapor deposition rate, the ion number concentration, and this just indicate if you work with WRF study or CM1 study, definitely pay attention to the Cooper parameterization, and we recommend to use the default of instead of using a default of 108%, we recommend 130%. Now, to sum up our first section on ice nucleation, the WRF simulation rely heavily on vertical velocity to be more positive and then to generate and maintain supersaturation in the convective system. And the Cooper parameterization in both CM1 model and the WRF model actually leads to too many ice crystals and too few supersaturation. And some of the ongoing work for ice nucleation study and convective study is going to be led by my student Katie and Ryan. So Katie is going to analyze the correlation between ozone and water vapor using the contrast data in the subtropics. And she is actually having some preliminary analysis between Merritt-2 analysis and the contrast analysis, and this is still ongoing. And Ryan just started his work, and he's going to do a survey on cirrus cloud using multiple campaigns. Now, the second part of my study is to show liquid, ice, and mixed phase clouds over the Southern Ocean. So we use this study to illustrate why do we care about simulation of mixed phase cloud over the Southern Ocean. Based on several previous publications and also this picture from IPCC 2013, the Southern Ocean clouds have very large cloud fraction over the whole year. It's usually around 80% to 90%. And the problem is, for this region, you can likely have the coexistence of all kinds of cloud. You can have ice cloud, mixed phase cloud, liquid phase cloud, and they can be right next to each other with very heterogeneous spatial distribution. But another problem is we have very few in-situ observation over the Southern Ocean. Until recently, in 2016, we had the Orcas campaign, and then in 2018, we just had the Socrates field campaign. On the other hand, climate model actually do struggle to simulate the reflected shortwave radiation over the Southern Ocean because of the treatment of cloud phase and the total ice water content, liquid water content. So here is a picture from the publication of Baldus Salcedo in 2016. You can see the bias in the TOA shortwave reflected flux, which is on the order of magnitude of 10 to 20 watt per meter square in this region. And this underestimation of the TOA short reflective flux could lead to a large bias in climate prediction, say on the order of 50 years to 100 years. And they also underestimate the cloud fraction and supercooled liquid water in this region. But the validation of the climate model over this domain is still limited by, as I said, few observations, in situ observations over this region. So the question we're asking is, how can we use in situ data to compare with GCM simulation? Is it possible we use something that is on the order of hundreds of meter scales to compare with GCM simulation, which is on the order of tens to hundreds of kilometer scale? The second question is, if we use co-located and nudged simulation, is it going to produce better result or closer result to the observed cloud microphysics? The third question we're asking is, what are the implications based on our comparison result for the parameterization of cloud microphysics? So the data set I use is based on the 2016 ORCA study that's happened in January to February over Punta Arenas. You can see the flight track of all 18 flights in ORCAs. We restrict temperature to below 0 degrees C in this study, and we can analyze a series of ice microphysical properties based on different cloud probes. On the other hand, when we compare simulation with the in situ data, we use two different types of simulation. The first one is a nudged and co-located CAM5 simulation, and this has been nudged for the UV 3D temperature towards the real analysis data, and the method is based on Wood et al. 2017. And we only output the CAM5 simulation to along the flight track, so it narrows down the sampling. The second type of simulation we do is a free running simulation. This one, we don't have any nudging. We only select this large domain right around where the ORCA's flights all happened in. So this contains a lot more sample, but it's not directly co-located on the aircraft. And both simulation we use about 0.5 by 0.5 degree with the MG2 cloud microphysics. So before we get to the comparison, the first obstacle we have is how can you define cloud phases in situ observations? This is actually not a very easy task. So we separated the definition to first separately define what is liquid and ice from fast 2DC and CDP. We use a couple of thresholds such as the number concentration, the maximum diameter, and the size distribution variability. After we define whether it's liquid or ice, then we can combine the ice together to get ice water content, combining the liquid together to get liquid water content. And please note that this is a method that we have to develop specifically for ORCA's campaign. Even though it is based on the idea from 3 previous publications, the different threshold has to be adjusted just to apply for the ORCA's campaign. And now come to the second obstacle. How do we compare something so small with something so big? So the small one, of course, observation from 100 meter to 250 meter, we actually did a scale-aware comparison for the observation, which is to apply a moving average from hundreds of meter scale to 20 to 50 kilometer scale. And that will become more and more comparable to the scale of a CAM5 0.5 degree simulation, which is 14 to 70 kilometer from 30 degrees south to 75 degrees south. After that, we have to find a mutual way to define cloud phase. So in the observation, we define cloud phases using the mass ratio of liquid water content divided by the total water content. When it is between 0.1 and 0.9, we call this as a mixed phase. Same idea is applied to CAM5 using the ice water content, liquid water content output from CAM5. Another obstacle is how can you compare the microphysics properties when you have something so small and so big. What we do is we use a grade mean quantity. That means when we do the moving average of the observation, the ice water content is average throughout this whole grid, regardless of it has in cloud, clear sky, or both. So it will become more and more different from the finer resolution to the coarser resolution. On the other hand, we use the great mean quantity directly from CAM5. So the benefit of this comparison is it try to do things more to apple to apple. Now, a demonstration of how do we compare is to use this time series. We have on the first row, which is the temperature, RHI, RH liquid, directly from in situ observation. And on the second row, we have the different scale of observation, averaged by 10 seconds all the way to 200 seconds, as well as the relative humidity from CAM5 collocated data. So the collocated CAM5 is in this dotted black line, while the other observation is in the color line. Then on the third panel, we have RH liquid instead of RHI. And then the fourth panel is where we define different cloud phases in the observation. So the cloud phase has the marker on the bottom, which has the green in mixed phase, red in liquid phase, and blue in ice phase. And the last row is the CAM5 defined cloud phase, which has the blue, which is all ice phase. From this example, there are a few things I want to point out. First of all, you can see by applying the moving average over plus minus number of seconds, you definitely have a smoother RHI distribution for the coarser observation. The second one is when you actually check our phase comparison method with the rise indicator, which is a good indicator for supercooled liquid water, it has these ramp up and down and ramping up and down. When it ramp up, it indicates existence of supercooled liquid water, and it matches very well when we actually find a segment that's either liquid phase or mixed phase, indicating there is supercooled liquid water as well. The third bullet point I want to point out is there is missing supercooled liquid water in this time segment around 1937 to 1941 UTC. So this is misidentified as ice phase in the CAM5 simulation. For the reference of the meteorological conditions, you can see this arrow just pinpoint this 20 minutes time segment. This is the hour-long, probably 8-hour-long flight track in one of the flight of Orca's campaign. And if you also check out the box that I just highlighted here, I want to show you this is what it will look like after we identify liquid phase, ice phase, and mixed phase using the 2DC imagery. So liquid phase has all these little dots that look like supercooled liquid water. Ice phase apparently has these large dendrites, and mixed phase has a column of ice, some small ice crystals, and then maybe some of these dots which are liquid phase in supercooled liquid water. So how much cloud phase in different type we see in the observation and CAM5 simulation? We separate the cloud phase into liquid, mixed, and ice. This box shows from 0 to minus 10 degrees C. The second one is from minus 20 to minus 10. Two things that we learned. One is there's definitely lower frequency of mixed phase samples in the CAM5 simulation. This actually corroborates the previous study that used satellite observation to compare with CAM5. As you can see, this is 3%, 4% in the CAM collocated data and domain data. And the observation show 19% and 38% from 1 Hz to 200 second average. But besides that, what is surprising to us is there is actually a higher frequency of liquid phase. And this is actually 60%, 70% in CAM5 compared with observation, which has 37% and 26%. The reason I said this is surprising is in the previous study, often people would quantify the difference between supercooled liquid water, the amount of supercooled liquid water between CAM5 and satellite data. And by doing that, it doesn't necessarily differentiate between liquid phase supercooled liquid water and mixed phase supercooled liquid water. So this actually may indicate in the future study we need to focus on not just the total supercooled liquid water, but actually in which phase the supercooled liquid water is missing in CAM5. Another lesson that we learned is the coarser resolution observation start to show higher frequency of mixed phase cloud. As you can see, this is 19% in 1 Hz data, this is 38%. Definitely by using a broader scope, you start to see more and more mixed phase cloud in that great mean. To answer the question, how much does the spatial averaging affect our microphysical properties? Does it matter if we use a 1 Hz data versus using a 200-second data? The answer is yes, they actually change the grade mean average quantity. So from the solid line to dotted line to dashed line, we get quarter and quarter. From the dashed line to dotted line to the solid line, we get quarter and quarter resolution. And the highest resolution, which is at 1 Hz, has the highest grade mean for ice water content and liquid water content. That is not surprising because if you average with clear sky condition, you get a lower value. And the other one we find interesting is all the trend, such as how the ice water content is decreasing with decreasing temperature, or how the number of ice is increasing with decreasing temperature. This trend is still captured in all scales of observations. Now, if we compare the 200-second average data with the CAM5 simulation, we have 2 sets of CAM5, just to remind everyone, a notched one and an unnotched one. And both of them show consistent result, which indicate that the sampling size of our comparison is not a main factor to impact our result. And both simulations show that liquid phase actually overestimate liquid water content, and mixed phase actually underestimate liquid water content, and the ice phase underestimate and overestimate ice water content and number of ice respectively. And this is consistent with the previous finding that Mayers et al. Parameterization in CAM5 actually overestimated the number concentration of ice. I think I'm going to quickly show you this scheme, which is a test of RH. So the take-home message is we find that the RH liquid peaks at liquid saturation for cloud fraction greater than 0.9. This is consistent with previous observations. But CAM5 lacks this RH variability. If you see, CAM5 has a very narrow peak around here, which is different from the wide range of RHI seen in the observation. And the spatially averaged observations are more similar to each other than compared with the model simulation. Looking at the supersaturation vertical profile, we found that CAM5 has too little clear sky supersaturation when temperature is below -40 C. And CAM5 also has too much cirrus cloud when temperature is below -40 C. So come back to the method, we're actually now developing another work to test the different ways to determine cloud phases. This is to give you an idea that there has been several previous studies that combined different instrumentations and different thresholds and develop their own method to define cloud phase. And this is not an easy job for individual data set, because for individual data set, you have to go back and test what is the optimal threshold to be used. So what we do is, based on what we show the comparison with CAM5, we are developing a separation method for the ORCAS campaign data. And you can see how many layers of algorithm we actually have to use. And the result is we can see ice particles, we can see liquid droplets, and we also provide a sensitivity test, which is something new that has not been examined before. To every individual threshold that we're using, we test how much is going to affect our cloud phase distribution. And all these different thresholds, we applied a sensitivity test. And this helps to link back to all the previous studies that arbitrarily choose their optimal threshold in their own data set. And we're currently preparing this as a cloud phase separation manuscript to be submitted to ACP. So quick summary on the second part, we find it's applicable to use in-situ data to compare with GCM. But we have to be aware that different scales of observation could produce different results. And the implications on the parameterization is we need to separate the supercooled liquid water quantification into liquid phase and ice phase and a mixed phase. And we also should emphasize the concentration in terms of number concentration, mass concentration, and how they partition in CAM5, not just say mass is controlled and then not to control the number concentration. So the third section, this will be a pretty quick one. So this part is about the surface PM 2.5 in California. This is a project that I'm doing as part of the NASA Health and Air Quality Applied Science team, which is called the HACUS science team. So I want to thank all my co-Is on this project, especially Frank Freeman Central from SJSU, Mohammed El Hamdan, and Akula Venkateshwar, who are our co-Is on this project. So what we do is we apply the MIAC and DART target, two different products from the Aqua Modis product to derive surface PM2.5 using the regression model and surfacing model. The satellite data is a columnar AOD distribution, and it's not very easy to link a column AOD to the surface PM2.5. After link this back to the surface, we use another dispersion model to downscale the distribution from kilometer scale to hundreds of meter scale and apply a daily average hourly result. And eventually, we blend these two fields, and we can provide a product that is more continuous in space and also more continuous in time. For a review paper that we're currently working on, this is a paper that I work with 20 different co-authors, and we are trying to give a guidance to the users who often download PM2.5 dataset for health-related studies. So this is the work that we compare CDC Wonder data, Dalhousie data, tracking network, all together. And the black line here is the EPA monitor. We can see not only they have different mean value, but also they have very different variability. And to show this in a more illustrative way, this is the map of the three data set compared with the ground monitor air data. So the black is where we have missing data. We actually applied a very strong quality control to the EPA data and only used the one that have both 4 quarters of data available. And by comparing them, we see CDC data has the large maximum over the eastern US, and the Dalhousie data has a relatively lower value, and the tracking network has a very high value in the Southern California. So all three publicly available data sets frequently used, and they still have large differences. Another tool that we developed at San Jose State is a visualization of the AOD. What we do is we use the ArcGIS website tool to develop this website. You can just log in this website. You can zoom in, zoom out. You can see where the hotspot is for AOD for a certain day. And for example, we have San Jose right here, and this is right around the San Jose airport. We have San Francisco, also the SFO right at this hotspot right here. We have Oakland and other cities where there are a lot of industrial backyard, and that has a high AOD correlated with it. And then we combine the 14 days in 2016 winter and get this composite analysis. And you can also go into this free website that we have, and you can see on average where do you often see high AOD. And another work is done by NASA Ames, Robert Chatfield, and Maytar, and they developed this quantile of surface PM2.5 to say where do you have the highest PM2.5 in the quantile analysis. So all of this can possibly contribute to a new AB 617 legislation that is currently undergoing at the California Air Resource Board. Now, for the other part of the PM2.5 study, we use dispersion model simulation to downscale it. This is an example of the downtown Los Angeles. We have two very busy highways intersect with each other, and we have Purple Air, which is a cheap, low-cost sensor that is deployed right around the intersection, which is at Jeffrey and Pepper. So if you remember these two locations, Jeffrey is closer, Pepper is further, slightly further away. And then we simulate this using the downscale model data. And we put in a specific emission inventory just for the line source of these two highways. And we get a slightly lower value compared with the observed Purple Air data. I'm not saying that the Purple Air data here is the truth, because there are still a lot of things that needs to be done about the accuracy of the low-cost sensor. But you can see the gradient is actually matched pretty well. You have a higher value for Jeffrey, higher value for Jeffrey in both model simulation and the Purple Air observation. And again, this website is publicly available. You can go into this link and play with it. You can see the last 7 days of our dispersion model simulation or the last few months of simulation. So to sum up for this PM2.5 work, we have found large differences in several publicly available PM2.5 dataset, and we show roadside enhancement in the visualization tool. And for the large spatial variability and temporal variability in California is still a main challenge to our relationship to derive PM2.5 from AOD. And for future work, we have recently received a Tiger Team #2 funding from the HACUS project, which is going to be conducting research on the wildfire event in California 2017. This is going to be led by Susan O'Neill from U.S. Forest Service. So, come to the end. I want to thank the funding from my NSF OPP grant and AGS grant, as well as the NASA grant that supports the HACUS project. And also want to thank all my collaborators here at EOL or other institutions, and also have discussed with many people here like Aaron or Laura Pan, as well as getting laboratory support from Stuart and Laura. And if you're interested in some of the links that are provided for the PM2.5 work, I'm very happy to share that with everyone, because one of the goals of that project is we provide the publicly available data set based on satellite information. And if you're also interested in other publications, please feel free to check out my website here, which is right on this left-hand side corner. And here are some pictures that we got from 2016 to 2018 summer at NCAR. In 2016, we stayed 3 months here. And this year, we stayed 1 month. And not only we get some really nice food and seeing what the aircraft is like, but also we get to do a lot of lab work. So I want to thank all my students. Some of them couldn't make it to NCAR because they have other internships. And I would like to take your questions. Thank you.
Thank you very much for this very nice talk. Any questions?
Hi, Minghui. Thanks for your very nice talk. So I have 2 questions for your first part. So in the first part, you show that compared with the RHI observations, the threshold for the Cooper parameterization in the model should be like raised from 108% to the 130%. So I'm wondering to what extent can these results to be extrapolated to other areas outside the observational regions? And the second one is that so you use the RHI observations to constrain the model parameterizations, and if you look at the other observations, for example, the ice particle number concentrations and something like that, could you get the consistent results or conclusions as the RHI observation? Thank you.
That's a wonderful question. So actually, for the first part, actually both questions were asked in a similar way by the reviewers to our paper. So the first part is how representative would this data set be to use this data set to adjust the RH threshold in the WRF simulation? So I have to say, yes, we are limiting in this study to the DC3 observations. But just by plotting out the RHI versus T type of figure, we have done that for HIPPO, for PREDICT, many other previous campaigns. The distribution of clear sky and in-cloud RHI all have a large variability up to 150%. It's not going to be capped around 108% like the Cooper parameterization would limit it to. So we haven't do an exact quantification using other data set, but for the limit of RHI that needs to be put up to a higher threshold would be consistent with other data set. The other question you have, gosh, I just paused for a second. Could you remind me what is the second question?
So if you use the other observations, say ice particle number concentrations, can you get the consistent result?
Yes, thank you. Actually, for the second half of the paper, we did the analysis on that. We not only tested how much number concentration it should have, is it consistent, is it better, but also we tested the evolution of the cirrus cloud from clear sky supersaturation to a fully developed clouds to a sedimenting cloud. And we find the evolution in terms of the evolution of RH, evolution of number of ice, they all actually are more consistent with the observation when you use the modified RHI threshold. So very good question, similarly asked by the reviewer too.
I'm not the reviewer.
No, I'm sure you're not.
Any other questions? Nobody?
Yeah, you can.
I have one question on your averaging of mixed-phased clouds. You show that by increasing your averaging scale, you increase your fraction of mixed-phase clouds. What does it mean for the microphysics? Because what may happen now that you average pure liquid water clouds and pure ice clouds, average them together, you get a mixed-phase cloud. But the microphysics, of course, is very different.
That is a very good question. So that is actually a main reason we conducted the scale-aware analysis. One reason is that we know there are different scales of observation, not only for model, but say if you have a satellite data, you have a larger gray box, you can only get a mean value inside the gray box, and you may not be able to see all the fine structures. What would happen to that kind of observation compared with hundreds of meter scale? So in the 1 Hertz scale observation, we do see these pockets of pure phase, say a thin stripe of just ice phase, a thin stripe of just liquid phase next to each other or blended together, or you can have a long ice phase and a long liquid phase with nothing else in it. So it would definitely misidentify these very heterogeneous segments if you average them out into a 50 kilometer. Then, of course, it will probably be defined as a mixed phase, and you don't really know. It's actually little pockets of ice and little pocket of liquid. So that is a problem. Probably we try to present it to the readers that to keep in mind, depending on what scales of observation you are choosing, you may get a result on your comparison result. And the CAM5 analysis may actually gain from this type of scale-aware analysis because using the parameterization in CAM5, we could actually put in some subgrade scale variability, such as the distribution of RH, and that is something we're hoping that maybe we can do one day, not just have one saturation of liquid for all the parts that ice and liquid is coexisting, but actually have this variability put in there. The other one is we can use these different scale analysis to show how much of a cloud fraction should be in CAM5 and how they should interact with each other. Is it like half of the gray box completely ice, half of the gray box completely liquid? Or maybe they're more like a chessboard that they have little pockets of ice, little pockets of liquid, and then they would, of course, interact more than just half-half separate that way. So all of these may give us some idea of improving the parameterization down the way. Thank you.
I've got follow-on to that. So when you say scale-aware, I mean, yeah, whatever, depending on what averaging length you use, you'll get a different answer. But is there fundamentally, or I guess this is an opinion question, do you think that there's fundamentally some minimum length scale at which you can say something is mixed phase? Like how close does a liquid water drop and an ice crystal have to be in order for it to matter to how you parameterize the microphysics?
That is actually going on the even smaller scale, Michael. That's a very good question. So I know that based on the 1 Hertz scale, it may not even be the finest resolution to define the pure pockets. There are studies that could show using a slower speed of an aircraft, maybe flying 50 meters per second, they can see pure pockets that way, and then in a 100 meter, you will have half liquid, half ice. So what would be the finest resolution we can reach towards to? That's probably can be helped by the holodeck observation to say in a volume, how much is the ice and liquid in the volume? In that little volume, okay, being distributed. But then it goes to the question of how much impact this being homogeneously mixed or heterogeneous mix actually going to have on the result. I cannot for sure say that do we want to parameterize a climate model using observation that's on meters of scale. But since now we are almost bridging the gap from hundreds of meters to tens of kilometers. Maybe taking a first leap to use the 1 Hertz observation would actually help us to get some idea. Yes, this actually go to how you fundamentally define mixed phase. Philosophical question, yes.
The differentiating between mixed single phase cloud, what's your comment on using remote observations? How good are they? Like you're talking about in terms of in-situ observations, what's confidence of remote observations?
That's a very nice question. Actually, that is kind of the status right now with mixed phase cloud study. On the one hand, we have remote sensing observations, often on the scale that is larger than the aircraft observation. A few recent study, though, like a study published by Thompson 2018, actually use imageries from if I remember correctly, it's a spaceborne imager that can break it down to 100-meter scale to see different cloud phases. But I haven't seen any study to validate that separation using in-situ observation. And some other remote sensing study, of course, would be very much inhibited if you have multi-layer clouds. Then it's hard to see through all the layers of ice and liquid phase intermingled with each other. And from the in-situ observation, we have to say there are a lot of multi-layer observation in ORCA's campaign. And then on the other hand, the in-situ observation is limited by you only have a 1D observation. But maybe the next step is finding a good comparative study where satellite data can be validated by in-situ observation may help to provide more understanding of that. Thank you.
Yeah, I have another following questions to Michael's comment. So I think one important reason to have this different cloud phases resolved in the climate model is that they could have quite different optical properties and which significantly change the Earth's energy budget. And I think my question is that when we talk about the scale average or scale awareness method, then it comes to me that maybe if you have a relatively large scale and you average all over the different cloud phases, you could get a similar energy radiative forcing or energy effect when you compare it with the using the relatively smaller scale average values. And so I'm wondering if you look at this, because if the relatively large scale results would work, then we probably would we don't need to go that much small scales, and it is probably not visible in climate models. Yeah,
that is another deeper step into this mixed phase problem. So there are two types of misidentification I think Tony you're talking about. One is what you're saying, if you have the same amount of ice water content, liquid water content, just how they're mixed up, heterogeneously mixed up with different pure pockets, or they are just a huge part of ice and a huge part of liquid. That is the spatial heterogeneity question. But another probably more major question right now we're considering is it would totally misidentify a long segment with a lot of supercool liquid water as a pure ice phase. That's what is shown in the time series. So that is easy to see that definitely would have a different radiative effect just depending on ice water content, liquid water content, and the ice number concentration, liquid water the liquid number concentration would be different. But I haven't actually quantified how much difference it would be if you have heterogeneously pure pockets of ice versus homogeneous distribution. It may not be as big of an impact radiatively speaking, but it would be a big impact on the time evolution scheme. Think about if you're mixed so well, the ice particle would very likely take in the water vapor from the air, and eventually using the WBF process, you will have liquid gradually dissipate and get into ice. But if you have a large liquid and a large ice, their interaction will be minimal. And then this liquid segment could stay longer. So maybe it's not only the instantaneous spatial distribution, but how mixed up they are could influence the overall time series, time evolution.
Okay. Thank you very much. Let me remind you, we have an upcoming talk on Tuesday. Leila Carvalho will be here, and she'll talk on the Sundowner Winds Experiment, SWEX first intensive campaign, understanding downslope windstorms in the Santa Ynez Mountains, Santa Barbara, California. This is next Tuesday at our regular time at 3:30. And let's thank Minghui one last time.
Thank you, Holger. Thank you, everyone, for coming.